Okay, so back to the notion of the difference between a wave description of light and photon description of light, right? Here's the key, right? Is that the photoelectric effect? If we're talking about the photoelectric effect, people assumed that something that was bright, okay, would have a large. These are electric fields. Remember, electric and magnetic fields. So people thought that bright light would cause the photoelectrons to be ejected faster, would have a big kinetic energy. And so the wave theory predicts that bright light will eject fast photoelectrons. Okay. Einstein's photon theory predicts that blue light will eject fast photoelectrons, right? The high frequency will, right? The intensity doesn't matter for photon theory. Color does matter for photon theory as far as the energy, right? Just because of this formula. For the wave theory, color doesn't matter and brightness does matter. Okay, so that's the big difference. Now, these are the predictions, and specifically, right, is that the kinetic energy of this thing. If you solve for the kinetic energy, it's all it is the photon energy minus the work function, right? And so the kinetic energy rises with the frequency, which is another way to say color, right? Okay. The intensity of light just ejects more. You'll have a bigger current, more electrons, but they won't have a higher kinetic energy. Okay. The wave theory, and this is a picture of light represented as a wave, right, predicts that the amplitude, right, if you make a bigger electric field, if this is bigger, right, then the electric field is what's ejecting the electrons, right? So therefore the kinetic energy will rise because the electric field will be bigger with a bright light. Frequency shouldn't matter, okay? Wave theory predicts that the frequency doesn't matter. So, the question is, what actually is the case, right? Well, the person to do this experiment was actually Robert A. Millikan, and there it is, right? This is the graph, a rough graph of his data. This is a graph of this, okay? So if you look at that, this F, this is like our x-axis, right? So that's like x. The slope of this is that, right? And then the y-intercept is, of course, a negative number, right? This is y equals mx plus b, slope-intercept form, right? This intercept is down here, right? Okay, so this is exactly what it is. Einstein's theory was exactly confirmed. It's exactly like that. This line has a slope. The slope is Planck's constant. This is how you would determine Planck's constant, right? There's the slope, okay? And if you look at this thing, obviously at below this cutoff frequency, photons don't have enough energy to even eject any electrons, okay? So no electrons are ejected, and then eventually you have enough to just pull them off of the metal, and what's left over, of course, can go to the kinetic energy of the photoelectrons, right? So there you go, right? There's your slope. And there's one more thing I was going to say about that, but I forgot. Oh yeah, I know what it was. Okay, so Millikan does this experiment. It's an exceedingly difficult experiment, and I have a 1930 copy of the Millikan's book, The Electron. In 1915, he writes this great conclusion, and he says, and he's trying to say all these theories, right? He says, the wave theory is straight out, and so-and-so's theory is straight out. The only theory that can predict the data that I got is Einstein's theory, and we know that's wrong. He just dismisses it out of hand, right? It can't be a particle, right? In 1930, the version of the book that I have, he says he changed the conclusion to read, the results confirm the now well-accepted photon theory of light proposed by Albert Einstein. Okay, so, there you have it.